So first of all, thank you very much for the opportunity to give this talk. And you could see from my title of my talk, I'm going to talk about two different topics. One of the topics goes under the name of high-energy QCD, and another goes under the name of integrability. And normally, integrability is something which you would associate with special class of two-dimensional quantum mechanical models. I don't need to tell you what QCD is. And basically, the idea of my talk would be to demonstrate that there is a very intricate relation between the two fields. And the talk is based on a series of papers which I have written with my brilliant collaborators, which are listed here. And before I will start talking about the content of my talk, I have to mention that in this list there is two very special names appeared. And these are names of the people that you know very well. And I think this is a very, very special occasion to remember those people, because both Lyudvik Fadeev and Lev Lipatov played tremendous roles in developing both the quantum field theory and QCD. So let's get started. There's no need to tell you that this year is special, and we are here to celebrate 50th anniversary of asymptotic freedom of formulation quantum mechanics, but there is yet another reason why this year is special, which you will see on my next slide. But as a first slide, many talks already, I don't need to repeat, that QCD is exceptional theory because it has tremendous success at describing physics both on small and large distances. And there's a lot of predictions, and I'm sure we'll hear more about the success of QCD in describing those phenomena. I will concentrate on only one example. And actually, this example was borrowed from the paper by David and Frank, which is written over here. And you may remember during the presentation by Tzvi, the first day, he said that just after appearing of these two parallel papers, there was two big papers in PhysRevs, which were very inspiring. And he recommended everyone to look inside and to see something very special. And this is what I did. And then if you go to this paper and you look for equation 520, you will find famous equation which tells you that moment of structure functions have dependence of Q-square, famous violation of Bjorken scaling, and as you know very well, it's controlled by anomalous dimension, shown here by small a and here by capital N, so there's some misprint. But what's important is there is a very nice one-loop expression for this anomalous dimension. And basically, the outline of my talk would be to say that this formula already knows about integrability. Simply, it took quite some time to realize that integrability is there. But it's just yet to illustrate that QCD is much clearer than you might think, and sometimes simple formula have a lot of information to deliver. And basically what I'm trying to show you in my talk, how you could start from that formula and go all the way to integrability. But at this stage, you could see that this formula, even though so simple, it was successful in describing, in this case, scaling violation, which was measured at here machine over Q-square, which spans 3 orders of magnitudes. So what was special for 2023? Another occasion to celebrate this year that it was exactly 95 years ago that Heisenberg wrote a paper in which he was trying to explain ferromagnetism in quantum mechanics, and he came up with very simple quantum mechanical models, which goes now under the name antiferromagnetic SXX model. And the idea was very simple. He looked for a very simplified model when you have bunch of particles, let's say electrons, which sit on the circle, each has spin 1/2, and here came up with Hamiltonian, which describes interaction of spins of those particles. And the simplest possibility would be just to take particles sitting on sign n and couple it with particles sitting near sides. So these Sn, these are spin operators, 1/2 Pauli matrices sitting on n side, and you'll sum over all those scalar product of spin from 1 to L, where L is the number of particles that sits on this circle. And as I said, these are simplest quantum mechanical models you could consider using those spins operators. And what's special about this model is this model turned out to be integrable. And actually, Beta in 1931 came up with a solution to this model, which from now on goes under the name of the beta ansatz. So this model, together with beta ansatz, it was the beginning of the new area of research, which goes under the name of integrable models. And integrable model is synonymous of considering the family of solvable quantum field theoretical models mostly in 2 dimensions, which have very special feature of possessing infinite number of conserved charges. And synonymous of this is that if you start looking for the scattering amplitude, the very fact that the model is integrable immediately implies that scattering should be elastic. So particles scatter without changing their momenta. They could only acquire a phase, which is exactly what's called S matrix. And it was realized a bit later that those S matrices satisfy fundamental Young-Baxter equation, which is schematically shown here, which is another way of saying that if you have 3 to 3 scattering, so particle momenta P1, P3 going to the final states, and you know the scattering is elastic, there is 2 ways how you could factorize this 3 to 3 scattering into product of 2 particle matrices. And this gives rise to a very powerful equation whose solution gives rise to the S matrix, out of which you could construct exact solution to those integrable models which appear in this context. And once you have such a definition of integrable models, immediately the question that you should ask, what's the relation between 4-dimensional gauge CD like QCD and 2-dimensional integrable models? It's not necessarily integrable, 2-dimensional models. But before I will start addressing that question, let me just give you some hint that there should exist a relation between 2 different words of QCD and integrable models. And the hint comes exactly from that formula for the normalist dimension, which you've seen on my first slide. There's a formula for the normalist dimension of twist-O operator with spin n, computed 1 loop level, so there's alpha s strong coupling constant, and here you have this function inside, which depends on the spin n, which is a negative integer number. Pay attention to the first term. So the first term has this innocently looking sum, which is called harmonic sum or d gamma function, which is logarithmic derivative of gamma function. And this function is, appears everywhere. Every time you start doing calculation of the normalized dimension of QCD, it appears almost every time. So this was development in QCD, goes to 1973. And meantime, in a completely different universe, which are integrable models, people start looking for the generalization of Heisenberg spin chain. So I told you Heisenberg spin chain, it was Hamiltonian describing interaction spin 1/2. And you may ask the question, what will happen if you start generalizing this model by going not from spin 1/2, but arbitrary higher spin representation? And asking the question, what would be the most general form of Hamiltonian, which is integrable, in the sense which I described you previously. And then it turned out that this Hamiltonian has exactly the same form as before. The only thing which will change, it will be interaction between 2 spins. Before it was just product S1, S2. Now for arbitrary spin, it becomes a function of this scalar product. And this function is related to the logarithmic derivative of the R matrix, which satisfies Young-Baxter equation. And if you go through the detail, you will figure out that this Hamiltonian turned out to be related to the very same function. So now if you compare equation over here, equation over there, you immediately see that the same function appears, even though interpretation of the argument of function is completely different. Here it was spin of the twist-O operators, and here is sum of spins of 2 particles which sit in inner ring side. But anyway, there is some coincidence. And what to do with this coincidence? At that moment, let me remind you of something which goes under the name of Landau paradigm, which goes back to Soviet time, and Arkady probably should tell me whether the statement is correct. Namely, the statement goes as follows. The logarithm is not a function, but a signal of some interesting physics. And as a confirmation for this, and I believe this was the reason for this statement, it actually came from computing of beta function QED in those days. So as you could see here, I put a beta function, and like you know very well, the periods of beta function with the right sign, it immediately leads you to asymptotic freedom. So this was exactly what Landau called logarithm is not a function. And now, given the fact that we're dealing with slightly more complicated function, let me kind of put forward improved version of this paradigm, which I try to argue later on. Every time you encounter d gamma in your expression, there's a signal of integrability. And I will show you that there is something behind the statement which comes from a particular example which I'm going to discuss. So come back to the questions which I put previously. What could be the relation between QCD and 2-dimensional models? And actually, this relation already had been discussed a lot during the conference. You know that if you go a strong coupling at large distances, QCD is expected to be string theory. A string theory is exactly 2-dimensional theory which we'd like to encounter at the end. The only problem, we don't know how to describe qualitatively this two-dimensional theory. So we have different indications either coming from the latest calculation is shown here. When you stretch it apart, have a quark, you have flux tube, which try to accumulate the way shown in the picture. You have Hooft expansion, and naturally leads you to the decomposition in terms of the Riemann surfaces. But coming back to QCD, let's try to put forward the following crazy idea. So if you do believe, and there is no reason why we should not believe, that QCD at large distances is indeed two-dimensional theory, this fact alone should have also manifestation at short distances. And if this is the case, there should be some additional symmetry which QCD should reveal already at short distances. So let's try to use this idea and see whether it's justified or not. And before I will start going to the hidden symmetry, let's summarize what are symmetries that we know of QCD. So QCD is four-dimensional Young-Mills theory with peculiar gauge group. And normally when you're discussing the symmetry, you start with the Lagrangian and you look for the symmetry of the Lagrangian. So what are those symmetries? There's a gauge symmetry, chiral symmetry, Korchemsky, conformal symmetry in the classical level. And then if you turn on interaction, you go to the quantum level, you know that almost all symmetry, except gauge symmetry, get broken by quantum fluctuations. And now let's speculate further based on what I said before, and let's play with the following question. Could it be that QCD possesses some symmetry, but these are not symmetry of classical Lagrangian? This is a dynamical symmetry, which means that they would not appear at the level of the Lagrangian, but they will appear only at the quantum level. In other words, start doing some calculation. In my case, it will be calculation PW QCD, and slowly we start to recover that something goes on. And why this idea is not crazy? Because we have example when exactly this idea is realized, namely it's additive correspondence. So in the case of additive correspondence, you're talking about a very special gauge theory, which is Maxwell subsymmetric Young-Mills theory. And you know that it's dual to two-dimensional string theory on very peculiar background. And this corresponds to be believed being exact for any value of the coupling constant. And if it's so, it would mean that if you encountered some symmetry on the right-hand side, namely if there is some symmetry of the this string theory, so this correspondence will automatically be translated to the symmetry of gauge theory. And indeed, we know that in the case of the additive correspondence, this new symmetry which appears with this correspondence is integrability. And therefore, it's quite natural, if you just extend this statement, just to look for QCD and see what are those symmetries. And I will try to argue, given 3 different examples, which will go one after another, that there are such kind of symmetries, and those symmetries intrinsically related to the symmetries of integrable models. So let's start with the first example. And the first example comes from the amplitudes. So let's start discussing scattering amplitude in QCD. And as a warm-up example, let's look for the simplest amplitude when you have external states which are on-shell glue on the physical polarization, and we look for the tree-level diagram. So at tree-level, the only particle which propagates in between the only glue, there is no sensitivity with respect to quark matter. As a consequence, these tree-level glue amplitudes are exactly the same as those that you encounter in any supersymmetric extension of QCD, including massively supersymmetric Young-Mills theory. So basically, in this situation, as far as 3 amplitudes are concerned, you're talking about amplitudes in generic supersymmetric, non-supersymmetric Young-Mills theory. So what happens? So if you turn on perturbative expansion, you will easily find out this number of diagrams which contribute to scattering amplitude start growing very fast. For example, here in this table, I just list a number of diagrams depending on the number of external lines. So you compute one diagram by another. Each diagram gauge dependent, but some is not. And if you sum up all corrections together, you'll find some miracle happen. Namely, in the particular situation which I'm considering here, namely, I'm talking about MHV amplitude when glue number 1 and 2 has plus helicity and all others have minus helicity, the corresponding expression, which goes under the name of Parquet-Taylor amplitude, is just very compact one. So it's given by this expression where the angular bracket stands for the contraction of spinors which depend on the moment of particles whose labels enters inside this angular bracket. And at that moment, you immediately ask the question, how could it be that such a messy expression, which will appear as the sum of so many diagrams, collapses into expression which looks so simple? And natural explanation, there should be symmetry. And indeed, there is a symmetry. And this symmetry is called dual conformal symmetry. Let me explain you why it's called dual conformal. And the best way to explain the origin of the symmetry and the origin of the name is to invoke the duality which had been mentioned by Roger yesterday, which is duality between scattering amplitude and Wilson loops. So how does the duality work? So on the right-hand side, on the left-hand side here, we're talking about scattering amplitude, including massless particles, let's say gluon, and you go to MHV situation. Namely, two gluons have plus helicity, others have minus helicity, and you not only stay at tree level, you just go deeply inside quantum, namely these S matrix take into account all quantum fluctuation inside. So per se, these objects now start to depend on the particle content, and therefore this amplitude depends on the theory choosing. QCD and equal 4 will be different. On the right-hand side, you construct an object which live completely different space. So this one was living in the space of on-shell momenta, and now you're constructing this object which lives configuration space. And these are light-like Wilson loop. So you take the contour, which is polygon defined by the position of its vertices, x1, etc., xn, and then you stretched segments between adjacent points, and you compute circulation of the gauge field along this contour. So this becomes Wilson loop, and it's light-like because all segments shown here in red goes a light-like direction. And once again, you compute quantum fluctuation, quantum correction to these objects using p-derivative expansion, and again, it depends on the contents of the theory. So in this way, you constructed two different objects which live in different spaces, depend on different set of the coordinates, and then what will happen, some magic will happen if you start to identify these on-shell momenta as a difference of those x's which enter into this picture. So in this moment, you start mixing two different representations. You identify momenta of particles as a difference of coordinates in this dual representation. And why it's important? Because as soon as you do so, some new symmetry will appear. Namely, if by any reason you will be able to show that these objects are related to each other, let's say they're equal to each other, then all symmetry of this object in configuration space, like conformal symmetry, will be translated into conformal symmetry of this object in the dual space. And this is exactly what the essence of the dual conformal symmetry. So as soon as the duality in place, it automatically implies that the regional amplitude will have to have a regional conformal symmetry, which is inherited from the Lagrangian of the theory, plus another dynamical symmetry, which come from this duality. And then, if you start looking for these two symmetries, you will find that they are not commuting. In other words, generators of these two symmetries are not commuting. You start to closing the algebra, and you'll find that algebra becomes infinite dimensional one. It becomes a Youngian symmetry. And the very fact that such algebra is infinite dimensional is synonymous that you have exactly the situation which you encounter in integrable models. Number of integrals of motion is infinite. The object should be uniquely defined by the symmetry. Well, this is so provided that you know that these objects are consigning. So how do you know that they are consigning? At that moment, some magic of adhesive T correspondence comes into the place, and basically you could show that as soon as you're dealing with n equal 4 theory, maximally symmetric ML theory, in the planar limit, this becomes exact statement. These objects indeed consigning for any value of the coupling constant in the planar n equal 4. Now let's go to QCD. Once you go to QCD, you immediately have a number of problems. The most important problems I told you before about conformal symmetry, dual conformal symmetry, but you know the conformal symmetry of QCD is broken. So therefore, there is no conformal symmetry per se, neither here nor there. So the question is, how then this object could be equal to each other? And then some miracle happened. Namely, if you now go to very special limit, when this amplitude describes the scattering of particles in very special kinematics, which is so-called multi-region kinematics, you could show that in this particular kinematic, these objects indeed consigning, despite the fact that conformal symmetry is broken. So what that means? It means that even though this dual conformal symmetry is the exact statement for n equal 4 theory, for QCD, even though it's broken, it's there, but only in the radial limit. And at this moment, you realize that something special about radial limit goes on. Once again, let me emphasize that this statement, which is shown here, it holds only a very special kinematic situation which is intrinsically linked to radial limit. And you, please. Yes.
So when you say QCD, you mean n equals 3?
No, it's also planar limit. Planar. Say again?
What do you mean by QCD?
By QCD, I mean NF goes to 0, planar limit. NF goes to 0.
What does it mean NF goes to 0?
Number of quark flare. In QCD, quarks is fundamental representation. If it's a top planar limit in QCD, simply if you formulate planar limit in QCD, as in conventional sense, so you have gluons, which are in joint representation, quarks and they join. As soon as you don't adjust number of quark flavors, contribution of quarks is sublinear in the planar limit. This is what I meant by planar limit.
But conformal symmetry is
Indeed, but let me emphasize once again that you start from n equal 4 theory. N equal 4 theory, conformal symmetry is exact. As soon as the symmetry is exact, Wilson loop equal to the amplitude for any kinematical values of this time invariance. Now you go to QCD. Conformal symmetry is broken. Duality doesn't hold for kinematical configuration arbitrary values of this time invariance. But if you go to radial limit, you will find that these two objects coincide. And both of these objects have conformal symmetry broken, both amplitude and Wilson loop. But the conformal symmetry breaking happens in the same manner for both, but only in the radial limit. So this was example number 1. Let's now go to second example. The second example has to do with exclusive process in QCD. So let's consider the simplex exclusive process when you want to scatter the proton of some virtual photon, and we go to the limit when the virtuality of this photon is very large. So basically, we want to get to the situation when this process could be described using the Parton model. And what Parton model will tell you, you could think about both incoming and outgoing proton as a collection of the 3 valent quarks, which in the momentum frame carries certain momentum fraction. And once you scatter of the virtual photon, you have to put 2 gluons to reorient original partons which were going along the momentum of PA into final stage momentum PB. And in this way, this becomes a diagram you have to analyze. And you could see from this diagram it involves 3 different blocks. One block, which is shown here in yellow, describes hot rescattering due to change of these 2 gluons. It goes to the hot function over here. And then you have 2 additional blocks which describe these non-perturbative objects, namely the possibility for proton incoming outgoing to be described by the 4 components with these 3 quarks. So these 3 non-perturbative objects give rise to what's called distribution amplitude, could be represented by a diagram like that. So in this situation, I just put arbitrary number of quarks, let's say n, small n, and these objects will depend on the momentum fractions of all those gluons, x1, etc., xn, which run from 0 to 1 and whose sum up to 1, and also some parameter mu square which has a meaning of the virtuality of each of these particles. And then QCD factorization that we have heard previously tells you that the probability of 4 factor corresponding to this process could be written as a convolution of those functions. Once again, hot function describe your hot scattering of short distances, and this function psi A and psi B, depending on momentum fractions of the partners, appear in the convolution with respect to their corresponding momentum fractions. There is prefactor 1 over q square in the power, which is dictated by number of constituents, and each of these functions which appears over here depends on mu. And this parameter mu has a meaning of the scale separating different physics. Physics coming at short distances sits in h. Physics coming at large distances sits in these distribution amplitudes. And as usual, we don't know how to compute an perturbative function. In this situation, it's a psi function. But we do know how to compute evolution of each of the functions separately with respect to the mu. And this already alone give you powerful information about codependence, dependence of this form factor, momentum transferred, which is scaling violation. So let's try to analyze this perturbative object which had a distribution amplitude and try to see how does it depend on this factorization scale mu square. And at that moment, you could come up with the following definition of this object. So there is 2 ways you could define it. If you're thinking about collection of partons as a collection of plane waves weighted distribution amplitude, you will get to this integral, which is just nothing else as superposition of those partons, each of them described as a plane wave carrying certain momentum fraction with distribution amplitudes depending on the factorization scale mu. And then there is another definition. Another definition appears if you're thinking about the same pattern from point of view of propagation of a light front. So you have light front, which move velocity of light, and you put on the light front those particles, which I denote here by quantum field phi, were located at the light front defined by a null vector n, and their position on the null front is fixed by parameters z1, etc., zl, which is just parameters defining the light coordinates. So in this way, this becomes very powerful expression because on the left-hand side, it defines matrix element which you may try to compute non-perturbatively. On the right-hand side, you have exactly this function psi which appears in our phenomenological expression you've seen previously. So now how to find dependence of this function psi with respect to mu. Very much the same way it appears for dependent elastic, dependence of the distribution amplitude on mu square is in one-to-one correspondence with the dependence of this matrix element with respect to normalization point. And why this dependence is non-trivial? Because here on the left-hand side, you have very single objects. So what happens here, you put on the light cone field phi, which could be either quarks or gluons, you connect it by the gauge link, but the very fact that they're null separated on the light front created some additional singularities. Those singularities are regularized by letter mu, and exactly this mu dependence which you want to capture. So how to find this mu dependence? So you don't a priori want to work with non-local object, which is this light ray operator. You have operator smeared along the light front. One possibility to avoid this problem, you could expand both sides of this relation in powers of z. So I remind you, the z defined position of the field on the light cone. If you go to the limit when z are all small, it's equivalent to the expanding of this non-local object in powers of the local operators. And those local operators looks like this. You have covariant derivatives in the power k1 theta kl. It's local Wilson operator, matrix element with respect to proton and vacuum. And here on the right-hand side, you will have the moment of this function. So this relation is exactly similar to the one you have with deep inelastic when the structure function, moment of structure function defined by the matrix element of twist two operators. But in this situation, it's more complicated because twist of this operator here on the right-hand side is defined by the number of insertion of field phi. Nevertheless, the logic exactly the same. You start looking for the mixing of those operators. You compute mixing matrix, which is shown here. And once you know mixing matrix, you go through the standard procedure of diagonalizing mixing matrix and finding its eigenvalues. So let's try to do it. And to be more specific, I want to specify my operator further. Namely, I have quark fields, which I decompose into helicity left and right. And the reason for this separation, because if you start with one of those operators and you create, you vacuum on the vacuum, it will produce it out of the vacuum instrumentum frame, the pattern whose helicity will be either plus or minus 1/2. So this error over here is nothing else indicating orientation of helicity of a corresponding part with respect to its momenta. And then let's start playing different games. For example, I could start with the operator, for example, baryonic operator built out of 3 quarks, and I choose each of these quarks with the aligned helicity. Another way, if I apply this operator to the vacuum, I will producing the baryon with the helicity 3/2. And then I want to understand how does distribution amplitude of this particular baryonic state depends on the scale. So once again, I look for the mixing matrix, I compute the mixing matrix, becomes some ugly expression, I diagonalize it on the computer, and finally I look for the spectrum eigenvalues. Here is shown. So on the vertical axis is a anomalous dimension of the mixing matrix. Horizontal axis is the number of derivatives which enter into your operator. So the first difference compared to deep inelastic is that because you have 3 fields and not 2, like deep inelastic, the total spin doesn't fix uniquely the form of the operator. Another way, for given spin, you will have possibility of distributing derivatives. Therefore, you have for given spin bunch points. So all those points correspond to different states, conformal operator, if you wish, which have different arrangement of the derivatives. And then if you just look for the form of the matrix in this picture, you immediately will realize that there is something goes on. Namely, you have ugly matrix, you diagonalize it, and you find quite a regular picture for the distribution of the eigenvalues. Let me also mention that those eigenvalues turned out to be almost double degenerate, and they have very nice structure you see in this picture. An obvious question is where the structure came from, right? Once again, just a result of the calculation, but once you have such a structure, you should have some explanation. And as I will argue on the next slide, this nice structure comes from a combination of 2 symmetries. One symmetry is conformal symmetry, which we discussed previously, and second is integrability. So how does it come about? Let's come back to the representation, not in terms of the local operators, but in terms of the non-local operators. So now I want to read seriously this non-local operator on the light cone. Once again, I'm taking 3 quark fields which are distributed on the light cone, defined by vector n, different positions z1, z2, z3, and I'm asking the question, how does operator depends on the UV cutoff, or another way of saying, how does the rotation operator act on this particular object B? So how you could do it? You start with an object like this, so you have 3 fields in the light cone, and you're introducing interaction. So what interaction will do? For example, you have a possibility of these 2 quarks to change gluon, or these 2 quarks to change gluons, or this. You immediately see from this picture the corresponding answer of the dilatation operator will be having very nice 2-particle structure, namely the contribution from each of the diagrams separately, which will be 1, 2 from here, etc., etc., etc. And moreover, you could compute the corresponding form of the operator. It becomes a very nice operator which has very simple physical meaning. Basically, what this interaction does, it doesn't move your particles away from the light cone, but it displaces particles along the light cone, changing position of Z1 and Z2 in way described by this integral. So in this way, you just have this formula over here, which tells you that this one-loop dilatation operator looks like three-particle Hamiltonian, right? I didn't specify yet how it looks like, but it looks like Hamiltonian acting on the light cone, and the light cone defined by the position of our particle on the light front. Well, now let's try to answer the question, how does this operator looks like? So we have conformal symmetry. And I remind you the conformal symmetry QCD is broken, but here the fact that you're dealing with one loop anomalous dimension simplifies your life, because conformal anomaly will enter into the game only starting from two loop. So the consequence is one loop dilatation operator, as you see in my previous slide, have to be conformally invariant. And another simplification happens because we're dealing with a very special situation when all fields on the light cone, and there is very nice collinear subgroup, conformal group, which leaves this light cone invariant. So full conformal group now reduces to its subgroup, and this subgroup basically is spanned by these regenerators. So these regenerators are responsible for the transformation of parameter Z. I remind you, Z defines position of fields of the light cone, and basically it corresponds to the Möbius transformation. And the corresponding generators are, so S minus, which shift your operator along the light cone, obviously this is symmetry, S0 corresponding to dilatation, and S plus to special conformal transformation. So these are what left over from conformal group if you specify your operator on the light cone. And then you could easily verify that these three operators, which are generator of conformal group on the light cone, satisfy a conventional algebra, which allows you to think about those operators as if they were spin operators. So now you have three particles. For each particle, you associate corresponding set of the operator, and in this way, you could think about three particles as each corresponding to a particular spin. So, for example, in this picture, you have three fields at point Z1, Z2, Z3. For each I define corresponding operator S1, and now my dilatation operator has exactly the form of this spin chain Hamiltonian, which we see in Heisenberg spin model. The only difference that instead of dealing with the Pauli matrices, we're dealing now with kind of unconventional representation of spin operator being differential operator on the long cone. And if you take this representation, you see that the number of sides of this spin chain is exactly the number of quark operators. And the spin operator, which you like now to identify within integrable models, are nothing else than generator of the collinear conformal group. So at this moment, we start from QCD, we went through calculation, we identify dilatation operator. Now we have kind of a natural map of dilatation operator in the spin chain, Hamiltonian. But the question, how does this operator looks like? So now you could take advantage of conformal symmetry, which basically tells you this two-particle Hamiltonian in virtue conformal symmetry should depend on two-particle conformal spin. And then you could easily figure out how does depend on this two-particle conformal spin. So you take S1, S2, the differential operator acting on the different sides. You take the sum of them, you define the corresponding total spin, you act on some test function, and from this you will find how Hamiltonian looks like. And what you will find is exactly this psi function which appeared in our previous slide. So I remind you this psi function for spin chain is synonymous you're dealing with an integrable spin chain. So this is a Heisenberg spin chain. Difference compared to conventional Heisenberg model that your spin operators, they are not SU2 spins, compact spins, but they are non-compact spins. And they are non-compact because they correspond to the generator conformal group acting on the light cone. So from this simple exercise, you deduce that for this baryonic operator, which we're considering, one loop dilatation operator could be identified as the Hamiltonian of the integrable spin chain. And once you said this, you automatically have a very powerful statement that anomalous dimension could be computed using beta ansatz. So, and here, just to flash you, I just give you a formula which allows you to compute exactly anomalous dimension using beta ansatz. If you do the calculation, you reproduce exactly this nice picture you've seen on my previous slide. So this was an example of this baryonic operator with helicity we have. But then you ask, what will happen if you start playing games with other states? For example, you have gluons with different helicity, you have quarks with different helicity. Now you could try to constructing kind of mixed objects. So for that one, the one which we discussed previously, when you have three quark operator with aligned helicity, we just seen it was a closed SL2 spin chain. So what will happen if you put gluons? So imagine I repeat the game. I put arbitrary number of gluons. Gluons are just representation. I could put as many as I like. And then you go to the planar limit, and you will find the planar limit corresponding dilatation operator also becomes Heisenberg spin chain. With only difference, you have to adjust the corresponding value of the spin at each side. You go on, for example, you may consider even more complicated object, which appears in the spin physics, which correspond to the quark anti-quark being at the end, in the fundamental, and the gluon in between. Doesn't matter how helicity or quarks are created, it's sufficient to have gluon helicity line. It will be also integrable model. And in this case, it will be open spin chain model. So far, so good. But now let's ask what will happen if I will go to a more complicated situation. So before, all helicity were aligned, but now I want to go to a situation when one quark has helicity which is down. So you have situation when two quarks are up and others down. In this situation, you will find that integrability is broken. And this breaking integrability also could be analyzed. It leads to some interesting effect like scalar dequark, but I'm not going to discuss this. But what's most importantly, if you go to very special limit when spin is large, you could show that actually integrability gets restored. So as soon as you go to a situation when spin of the operator is large, anomalous dimension will have universal behavior, which is logarithmic in spin, and this is synonymous of having semi-classical limit over spin chains. So this is a second example. And now let's go to the third example. And the third example is exactly this radial limit, which already appeared on my first slides. And we already had very nice talk by Gabriele and Raju, so I don't need to repeat a lot of what they have said. Basically, what we're trying to do, we're trying to find a scheme which would allow us to describe the growing cross-section, growing at some power of the energy, using the conventional techniques that we have, in this case, perturbative of QCD. And the first attempt was done by BFKL. And the idea was to start with computing perturbatively scattering of two objects, trying to identify class of large corrections. And those large corrections appear as a power of the logarithm of the coupling constant, accompanied by powers of the coupling of the logarithms. And then BFKL Pomeron appears if you sum up those corrections to loop level. And what you will find exactly this behavior, power behavior, which Raju flashed. Namely, BFKL Pomeron appears if you're summing infinite class diagram like that. So what you have here, you have two vertical lines which correspond to the propagation of so-called region, which could be thought like gluon dressed by virtual corrections. And propagating a T-channel, these regice gluons interact with each other by exchanging normal gluon. Each of these rank gives rise to the logarithms, but if you sum them together, there's some exponentiation which finally leads to the power rise with the power which is 4 log 2 times the coupling constant. And this rise is a bit too much, so you have to include some additional corrections to satisfy unitarity relations. And one way how you could do so, you could impose the unitarity conditions S channel. So if you impose unitarity conditions S channel, this is synonymous of iterating over a number of regice gluons propagating T channel. For BFKL Pomeron, these were just 2 regice gluons, but if you impose unitarity, you have to include arbitrary number of regice gluons, and then some respect to them. So the lowest contribution will be like BFKL. You have 2 regice gluons, but in principle, the number can be arbitrary. So now if you look for this diagram, if you're thinking not about S channel, but in T channel it has very nice interpretation as if you had these n regice gluons propagating in T channel and having pairwise interactions with each other. So this interaction kind of special. Namely, if you're integrating over momentum flowing along horizontal line, you can convince yourself the leading contribution, meaning the one which enhanced by powers of the logarithms, come from very special kinematical configuration region. Namely, it will be the region where rapidity of these gluons will be ordered if you go from upper part diagram to the lower one, but transverse momentum of this gluon could be arbitrary. In this way, taking advantage of this fact, you could reinterpret the rapidity of these gluons like evolution time in T-channel, and think about this diagram is if you had n particles propagating in time in T-channel and having interaction which take place on 2-dimensional plane of their transverse momenta.
But here you gave up large n.
It's fine at n. It's fine at n. Now let's do large n. And once you do large n, you will some simplification happen. So once you go to large n, this diagram, which you see in my previous slides, could be expanded systematically in powers of some planar objects. And the leading contribution will come from the diagram when, for example, particle number 1 could interact only with particle number 1 and particle n, etc., etc., etc. And if you just look carefully in this diagram, you will see it has topology of cylinder. And this is exactly the same cylinder that Gabriele was talking about. The difference between his cylinder and this cylinder is built up out of elementary excitation, which are gluons, whereas in Gabriele's case, it was an perturbative cylinder, which was built out of the strongly coupled particles. But what's in common between the two, this cylinder, once again, describing propagation of particle in T-channel, evolution time defined by the total logarithms of the energy, and the corresponding interaction described by some kind of effective Hamiltonian. So this calligraphic Hn corresponds to the interaction between nearest gluons in this picture. And you could show that after summing all those contributions, it exponentiates into something proportional to log of the energy times the Hamiltonian, and this naturally becomes power of the energy. But what's unusual here is this power rises in the power which is operator describing interaction of the gluon. So now if you want to compute this object exactly, you have to diagonalize the Hamiltonian. In other words, you have to solve eigen problem for this Hamiltonian. And let me remind you that these states, they live in two-dimensional space. Therefore, after Fourier transformation, they become depending on two-dimensional impact parameters Z's. But Hamiltonian is still there. And this Hamiltonian has nice two-particle structure, exactly the one you see here. So this equation has the name of Bartley-Kvichinsky-Pashalovich equation. It involves complicated Hamiltonian, which you have to solve. And if you knew how to solve this equation, you could expand this object in power size eigenvalues to get very nice representation as sum of its eigenvalues at each particular eigenstates will give rise to the Regge behavior, which intercept defined by the energy of a corresponding Hamiltonian. And now integrability comes about when you realize that this Hamiltonian, the one describing these diagrams, turned out to be integrable. Not only integrable, it becomes equivalent to so-called Heisenberg SL2C spin chain. So this C here has to do with the fact that we're now dealing with two-dimensional transversal momentum, not one-dimensional as a light cone. So now you have this identification. It's sufficient. You compute these energies, and basically now you have very compact representation. It turns out that this problem becomes very complicated. This Heisenberg spin chain has never been analyzed before, so we had to suffer a little bit, but we did some calculation, and what we found at the end, something interesting. Namely, if you remember from Gabriele talk, consequence of his consideration was this energy, let's say the intercept of those diagrams corresponding to cylinder, should go to 1 as a consequence of this bootstrapping condition that he described. And now what happens here is that if you do calculations, you look how this energy depends on the n, and I remind you, n could be thought like a number of vertical lines here. We did found that these energies go to 0 when n goes large. So somehow we have this quantitative agreement between the two, but in our case it comes as a result of a very non-trivial calculation. And honestly, we don't understand the reason. So finally, let me come to the conclusion. So I promised you at the very beginning to show that there is intrinsic relation between QCD and integrable model, and indeed, I have shown you that not QCD, but effective QCD dynamics turned out to be integrable in 2 different limits. So one limit was when you look for the scaling dimension of the distribution amplitudes, which effectively was dynamic on the light cone. And we've seen in this situation, QCD dynamics turned out to be described by Heisenberg spin chain defined on the light cone, which was SL2R integrability. And second example was Regge limit, in which case it was completely different objects, scattering amplitude and Regge limit, and we arrived with more or less the same integrable model. So now a couple of questions. So I told you that one of the ingredients in my calculation was conformal symmetry, and conformal symmetry QCD is broken. So the immediate question to ask, what will happen if I start going to two-loop, taking seriously in account contribution to conformal symmetry breaking? And the first surprise, it turned out that at least if you go loop by loop, integrability survives conformal symmetry breaking. Another question which is related to what Zohar asked previously is that we always were dealing with the planar limit. So what will happen if you go beyond planar limit? And the answer, integrability get lost. So somehow integrability needs planar limit. And last but not least, QCD is a very special theory, but you could imagine that if you're now going to supersymmetric extension of QCD, the more symmetry you put, the better situation becomes. And once you come to the maximum supersymmetric angular theory, when you put in maximum supersymmetry as possible, you enhance all symmetry, and therefore integrability should be enhanced. And indeed, in this case, it is known that integrability holds, for example, for dilatation operator, not on the light cone, but for complete dilatation operator. And finally, I come to the conclusion, and basically conclusion is that I have shown you there is integrability, but you don't understand the origin. Basically, the way how integrability was found by doing the calculation. But once you have kind of experimental data, you need explanation. So the main question which I leave for years to go, hopefully for the next University of QCD, to understand what's the origin of this phenomenon which I described you during my talk. Thank you very much for your attention.
Okay, just keep it. So, thanks very much for this beautiful, clear talk and the questions, right? So,
yeah, you described the cases where the number of sites in the spin chain is fixed. Are there examples of integrability where you mix different? Because when you study operators, right, you'll mix operators with different numbers of.
You're talking about the
partons.
limit when the number of operators becomes large? Which limit you're talking about?
No, just say if you study the structure of an operator made of gluons, right, you'll pair create gluons within the operators. So.
You're talking about
Like-
mixing. You're talking about possibility of
Yeah,
connect with each
mixing of different bit numbers.
Yes, it's
That's not suppressive and at large n, right?
no, it's not suppressed at large n.
So are
But,
there integrable examples where this mixing is taken into account?
So you remember this anomalous dimension which appeared on my first slide? It was exactly anomalous dimension which fits into the example. So if you have a dependency structure function, you look for the scaling dimension of dependency structure function. You go to the singlet channel when you have quark, anti-quark with the same flavor. It mixed with the gluon operator. So you have mixing metrics. So quark operator could mix with gluon operators. And then you could degeneralize the mixing metrics to find the corresponding anomalous dimension. Those anomalous dimensions, they are not given by psi function. It's much more complicated expression. Therefore, they're not integrable. However, then you ask the question, what will happen if I go for large values of spin? For large values of spin, this anomalous dimension will have the same behavior as integrable sectors. It will be log of the spin. And basically, this logarithmic behavior of anomalous dimension for large spin is a universal feature of anomalous dimension in all gauge Cs, including n=4 theory. The difference between n=4 theory and QCD is a prefactor, which is cusp anomalous dimension. But behavior is the same. I don't need to tell you that in n=4 theory, this behavior corresponds to the GKP string rotating in the DS space. Log S appears because strings get stretched and start to fill the boundary of the space. But in QCD, it's the same behavior. And therefore, my immediate question would be, where the behavior came from?
By the way, just a small remark. You quoted Landau. I think there was also a quote when Landau said, chicken is not a bird, logarithm is not an infinity.
Well, very good, very good, very good, very good, very good. I have different, I thought that Arkady would be the person because I wasn't born by the time the statement was made. But there are some people, I hope, that still remember the correct statement.
I just looked it up on the web.
Okay, so my remark, more than a question, is that the difference between what you are doing and what I was presenting is that I'm doing planar unquenched QCD. So for me, and I play with this fact that there are quark loops in the game, in particular to bootstrap the region, and then to argue that the Pomeron has to be to have intercept near 1. Now, instead, in your case, if I understand correctly, the intermediate state in the S channel is just 2 heavy strings.
In this channel?
In the S channel, the intermediate state, if you cut your cylinder, it's just 2 heavy. It's like in perturbative string theory where you have the...
But you know by the first of all...
so my question is whether you think really quark loops will spoil things if you stick to planar?
Yeah, I understand. First of all, as I tried to emphasize, quark loop, in principle, you may include quark loop in the consideration. But what will happen first, the quark loop will produce contribution which is not as leading as the one coming from the gluon. Basically, the contribution which I presented here, it was special from point of view that you were selecting contribution which have a maximal power of the logarithm of the energy per coupling constant. Quark loop do contribute, but their contribution is subleading.
In energy, you mean?
in energy. But you can include it. It will be kind of systematical expansion, subleading correction. So therefore, assume at the moment I will include quark loop, I have to add to my picture some infinite class of subleading corrections, which I didn't discuss yet. So they will appear as additional correction to those formulas which I presented here. However, let's come back to what you said. What I did, I basically repeated your argument from your paper. Namely, I started from the cylinder diagram. So I will repeat exactly what you said. So I start from the cylinder diagram. I will cut it in two. So I want to play the game with this bootstrap. Namely, I want to think about this cylinder as being obtained by gluing together two open wall sheet.
Yes.
Yeah. So imagine I will repeat exactly the same what you said. I just cut the cylinder by two, and I start gluing together these two objects. And then I will start with, if I go through the same analysis you did, associating with open string wall sheet some intercept, and writing the formula, exactly the one which you wrote, I will come to the conclusion that this closed string intercept will be related to intercept with open string.
Okay. But so you said that the eigenvalues go to 0.
So this
large n.
Yes.
That's what you said.
So this n you could
Simple as he was saying, you have to sum over n.
exactly.
And so you have to
Once
see
again,
whether the sum.
indeed. At that moment, you run into a problem, which is a very serious problem, because as I told you, these ENs, these are eigenvalues of certain integrable model. It happens that this community of integrable models, such kind of models are new, because they're non-compact, because this two-dimensional plane. And it happens that for non-compact models, basically most of the techniques that people developed since Heinsberg paper is not applicable. So we have to work out new techniques. So this is a very interesting problem. I know that many people working on this, trying to understand how to compute analytically those energies for large values of n. But what I told you is the fact that it goes to 0. It's based on a finite number of numbers. Basically, we're computing the n up to n8, and we see that there is a trend going to 0. But you're perfectly right. We have to sum the series. This is a next step complexity problem.
Thank you. I have a question about the duality between the Wilson loop and the scattering amplitude, the equality, I would say. These two objects, they have both infrared divergences,
No.
right?
Only one has divergences of red, another has UV divergences.
So, sorry, the scattering amplitude has infrared divergence.
We agreed on that.
Sorry?
Wilson loop has UV divergences. So this object here,
Right. So there is an infrared divergence that is mapped to the UV divergence. Could you comment a little bit about this? Is this a technical prescription, or is there some fundamental understanding on how one gets from the UV of the one to the infrared of the other?
so there is no, to answer your question, there is no derivation, but there is qualitative understanding why it should happen. And this qualitative understanding comes from, unfortunately, from idea CFT. So if, once again, this duality relation, okay. So this duality relation between Wilson loop and amplitude is completely counterintuitive. But it's not completely crazy. Why it's not crazy? Because it was known already quite some time that infrared divergences of scattering amplitude are in one-to-one correspondence with UV divergences of the cusps of Wilson loop. So therefore, if you're comparing these two objects, amplitude and Wilson loop, you already knew before doing the calculation the divergent piece of one should be equal to the divergent piece of another one. The essence of the statement of duality is about finite path. The fact that finite path matches, these are what non-trivial about the statement. But finite path depends very much how you introduce UV cutoff for the Wilson loop and infrared cutoff for the amplitudes. So at the moment you're saying that UV cutoff twice the infrared cutoff, you're modifying the finite path. So therefore, identification of UV cutoff and infrared cutoff is something which comes in addition to this picture, if you view it from point of view of UV coupling expansion. The identification between the two came from strong coupling. So if you go to unequal facility to strong coupling, there, this duality appears as results of so-called T-duality. In other words, there is some transformation which you do on one object in this IDCFT representation, which maps you into another object. And it's this transformation which will tell you that actually UV cutoff of one object is 1 divided by the infrared cutoff of another object with some constant in the numerator. But these are not quantitative statements, it's qualitative statements. To find it, make it qualitative, we have to do the calculation, And the constant which appears in the numerator should be computed from explicit formulas, and which has been done.
Yeah, so maybe a short discussion with you and
Very short. Yeah, no, just because it's kind of philosophical questions that you said that what is the origin of integrability? I was interpret what you said that there is no integrability in QCD because you are sure.
No, once again. I just to make statement not to be misled. QCD is not integrable model.
Yeah, no,
But we agree that there is certain limits. Some effective dynamics of QCD is integrable. This is what I was saying. I'm not talking about QCD, I'm talking about...
I understand, but in this way, you can discuss that, let's say, start from integrable piece and then try to discuss the deviation from this.
Yes, yes.
It would be interesting to go
Yes.
this way.
I didn't have a time. We did it for anomalous dimension. I could tell you privately the answer. This question had been addressed at least for one of the examples I gave.
so thanks very much. It was very interesting discussions also, but we should go ahead. So thank Gregory, this beautiful talk.